Hello everyone, we're doing lecture 13, example 1472. This is not the practice problem from your textbook. I actually pulled this example from another textbook. This is a very classic energy conservation question related to with a combination of the energy analysis and force analysis for circular motion. As always, please make sure you read the question before proceed. We have a roller coaster car that has a mass 700 kilograms given, including its passenger. If it starts from top of the hill A with a speed given as VA at 3 meter per second, determine the minimum height h of the hill, which is right here, so that the car travels around the inside loop without leaving the track. Of course, for the safety reason, and we will be neglecting the friction. The mass of the wheels and size of the car will neglect all of them, which essentially means this car can be treated as a particle. What is the normal reaction on the car when the car is at B and when the car is at C? Of course, after we calculate the H, we'll determine the reaction force at B, reaction force at C from the track supporting the cart. We'll take the radius curvature rho B at 7.5 meters and rho C at 5 meter. So first of all, visualize the motion. Where does it go? This is dynamic, so first of all, visualize it. So we'll have a card go here, and then here, and then finish. Okay? So we're given with the mass at 700 kilogram, velocity at A, 3 meter per second, radius of curvature, 7.5 meter at B, and 5 meter at C. So what does it mean here? Without leaving the track, but we want the car travels around the site without leaving the track. Okay, so what is the tipping point when the car will leave the track? So imagine here, if we do not have enough speed, then this car will never go up to the top, right? If we have enough speed, of course, it will go through B and go through C. So there has to be a critical point that distinguishes whether I'm going to stop right here, start to roll back, versus I'm going to going through B and going through C. So what is happening at point B? Or at the same time, what is happening at point C? This is what you want to figure out. So we'll start with the free body diagram here. And this free body diagram can either representing B or C. It doesn't really matter. So let's say we're looking at point B. When the cart at point B, what is the free body diagram? Start with G, gravity has to be there. G and EF. Next is normal force. Okay, at B, when the car is rushing passing B, where does the normal force coming from? Coming from the track, supporting the cart, right? So otherwise, imagine without the surface here, your B would be going out of the track, right? So B, the track at point B, this tangential line is giving your cart roller coaster a normal force. So we have Fn that is coming from the track. And we don't need to worry about friction, and there's no any other external force. So G, N, E, F. We don't have E, we don't have F. We have G, we have N. That's it. Okay. For circular motion, we want an NT system. For the NT system, N would be pointing towards the center of curvature. So apparently if we're looking at B here or C here, you will be looking at towards the center. So naturally, I'm setting up my N direction positive pointing down and my T direction the same as my traveling direction, and which is VB or VC. Okay, so we're looking at either B or C. So we will be having a force. Remember, your normal acceleration is the reason why your direction of the velocity is changing. So remember that we have AN equals to V squared over rho. Right, so the sum of forces in the N direction is the reason why you have an AN, you have a normal acceleration. So therefore, we're going to do a sum of force in the N direction equals to MAN. We'll get Fn plus mg. Okay, remember my N positive direction is pointing down, so Fn is pointing down, my mg is pointing down, equals to mv squared over rho here. Okay, now let's take a look at the relationship between the velocity and the force. When your car goes through B with a very large velocity, so that means this is very large. Your m is fixed, your rho is fixed, your m is fixed, your g is fixed, okay, unless you're somewhat changing the gravity, right? Okay, all these are fixed. So we have two variables here, Fn and the velocity. And Fn and velocity, they are proportional, or they are not linear proportional. Right? Of course, there's a v squared here. So if you have a super large speed, your velocity is very big, then that means your Fn is very big. Okay. On the other hand, if you do not have enough velocity, let's say your velocity is not enough, it's small. That means your Fn will be small. However, how small is small? Okay, when you go through this point B here, there is a scenario that this car is almost going to leave the track, but not leaving the track yet. And that critical point is you do not have any normal force, right? That means your velocity is small enough. At that point, your Fn is equal to 0. However, at that critical point, you're going to pass point B without problem, because anything smaller, you would not have any normal force. That means you either won't get up to B or you're going to fall down. So when Fn equal to 0, that is your minimum velocity required for your roller coaster to pass B. Therefore, we'll have when Fn equals 0, when there's no normal force, we'll find the minimum velocity at point B. Right? For those of you who are familiar with the experience, this is called the 0G experience, when there's no normal force that is acting on you. Okay, given that, we will take this here when Fn equals 0, rewrite this, we'll get to V equals to square root G and rho. And this rho will sub in either rho B or rho C. You will be calculating your velocity, or your minimum velocity at B and at C would be 8.58 meter per second and 7.00 meter per second. Right, so these are the minimum velocity that required for you to have a teeny tiny little bit normal force at B or C, like almost going to be 0. Anything smaller than that, let's say 8.57 at point B, you will have no normal force and the car will leave the track. Okay, so we want to find the height h from A to B. Using the energy equation, we need a datum for our potential. So we'll set our datum here. From A to B, no friction loss. Therefore, from A to B, we'll have the kinetic energy at A plus potential energy at A equals to kinetic energy at B plus potential energy at B. Okay? We start with the initial velocity, 1/2 mva squared, and we have mgh. This h is your starting height at point A. And 1/2 mvb squared plus mghb. And this hb is given. And this vb will sub in the vb minimum from the previous page. So subbing the number here, times 9, plus 700. Yeah, I thought I made a mistake in my solution, but you can see the mass is going to be canceled out throughout the equation. So we only have 9 here, 9.81 h 1/2 vb square 73.6164. I'm just keeping more decimal places here. 9.81 times 15. Okay, and we'll get this h equals to 18.29 meter. Okay, usually it's safe to stop here. This is your height, the minimum height for velocity b at B to get that minimum velocity, and for the velocity at point C, get the minimum velocity. However, we can check that. We'll just quickly check it. We'll check if the height 18.29 meter will give us enough speed to pass point C or safely pass point C. So we'll do the same thing. TA VA equals to TC VC. This is 1/2 mva squared plus mgh. Now this h can be subbed in by 18.29 meter. This is the height you calculated. Equals to 1/2 mvc squared plus mghc. Okay, we'll have 1/2 times 9, 9.81 times 18.29. We got it from here. 1/2 vc squared, we don't know, plus 9.81 times 10. We want to check whether this velocity c given by the height 18.29 will be enough, or in other words, has to be greater than the minimum velocity vc that we calculated on the previous page. And we'll have this velocity here, 13.10 meter per second. And if you recall from the previous page, the velocity at point C minimum is 7 meter per second. So this is greater than VC minimum. So we're okay. That means now we can safely declare this is our answer. The minimum height for the roller coaster to gain enough speed to pass point B on top and pass point C on the top. Lastly, we want to calculate the reaction force, or what is the force that is acting on the cart at point B and point C. So at point B. And we'll do it at point C as well. So remember our free body diagram. We have mg, we have a normal force, okay? Our n direction is pointing down, and our t direction is tangential. Okay, this is our NT system. So at point B, remember point B is we're using the critical point when you experience 0g. Right? So you're going to just have enough teeny tiny that minimum velocity to pass point B, to safely pass point B. So at point B, we are already going to get it. Our normal force, this part, going to be 0. Right? So this is what we call the 0g. 0g effect. And then at point C, we'll do sum of Fn equals to man. You calculated the velocity at point C, given that 18.29 meters, the minimum height we calculated using velocity b minimum. We have nc plus mg equals to mvc squared over rho c. All these are given. nc, m, 13.1 square, the velocity, divided by the rho c, 5 meters, minus 9.81. And the mass is 700 kilograms. Our nc can be calculated, 17,158.4 Newton. We got our reaction force at point B, which is 0, that when you're experiencing the 0g, and 17,000 newtons at point C. So that's a very large force. Right? That's what you experience on a roller coaster if you have been on the roller coasters before or a fan of roller coasters. Okay, that's it. Thank you for watching. I'll see you next time.